All right, so last time, or the last couple of classes, we studied the solution for the free vibration with viscous damping. All right, and we saw how to derive the equation for the different cases: overdamp, underdamp, and critically damped. All right, today, in order to follow the same procedure, we're going to do the same thing, but it's a lot faster for the free vibration with Coulomb damping. So free vibration with Coulomb damping, and that's also known as the dry friction damping. And the reason I do this is because it's a little bit different than the viscous damping on the derivation. All right. Okay, so we saw that the Coulomb / dry friction damping so that's the one you use in statics, is given by what? Mu, certain coefficient mu, a static or kinetic coefficient, times the normal force. And in most cases, this is equal to what? Mu times the gravitational force times mg. So this is just a reminder to what we saw before. Okay, so let us consider, as an example, just one single degree of freedom. So let us consider the below system, where you will have just one mass with one spring. So we have the block sliding on that surface. So this is K. Okay, and obviously in this case, we're gonna have here the friction between the block and the ground. All right, so we need to do what is the procedure in order to derive the equation of motion? We need to follow the procedure. The first thing is always to do some type of figure. All right, so step one. Figure or sketch of what is happening. All right, so here we have two cases because the friction force is going to have an opposite direction in both cases. So once you pull the block to the right, what's going to happen? The friction force is going to go to the left. But once the block is being pulled back by the spring, now the friction force is going to go to the right. Yeah? Okay? So let's do those two cases. So let's see. Put some space here. Okay, let's call this one. This one. Case 2. All right, so on the first one, what should be the forces? You have gravity mg, you can have the normal force, even though we're not going to take too much into consideration that. Then, if the object is moving to the right, we have mx double down in direction. What should be the direction of the friction force? Should be opposite to the motion, no? So it should be going to the left. So it should be, so we'll have here, we first have the force of the spring Kx on the opposite direction, but at the same time, we're gonna have the friction force here in the opposite direction equal to mu sub m. Okay, so this is the time that the block is going to the right. Now, the other case, so we're gonna have basically the same figure, mg, and okay, x, but now friction force will be on the opposite direction. Okay, and hold on one second, I'm going to explain something. Something I forgot to put here. Every time we're going to write down an equation, we need to specify an origin for the coordinate system. So let's say our origin for coordinate system would be this one over here. Okay, so in here, I think it's easy if I do it this way, okay? I put it this way over here. All right, you might be confused here because you saw that I still do mx going to the right and mx going to the left, to the right, no? And kx and kx, okay? And the only thing I changed is the direction from mu sub m. The reason is because this is working back and forth, all right? So x is the only thing that is related to the current system. So let's just use the normal sign convention when I put positive going to the right. But now what happened to the friction force? Is the friction force in function of the deformation? No, the friction force is just going to be in function of what? Mu, the drive friction coefficient, or the kinematic friction coefficient times n, and n is equal to what? Mg, no? So that's absolutely not related at all to the current system. Agree? Okay. So that's why I'm just specifying that this would be the different one, and the rest I leave it like on the general current system. Okay. So that's really the two cases we can have when the object is moving. So now, step 2, always the same thing. Step 2. Write equations using, in this case, what type of motion are the objects having? Just translation. So the only equation we need is summation of forces equals to MA. Okay, so if we do that in case 1, and in case 2, what do we have? So we'll have over here minus kx minus mu times n equal to mx double dot okay, and this one, I'm going to do it right away. Okay, I don't think it's difficult. You all see that n here will be equal to mg, no? Once you apply summations on the y. So this equation will actually simplify to m x double dot plus kx plus mu mg equal to 0. And for case 2, we have basically the same thing. The only thing that changes is the mu sub n, so minus kx plus mu sub n equal to mx double dot. So this is equal to mg. So we're gonna get mx double dot plus kx minus mu times mg equal to 0. Okay, so basically you see that the equation is exactly the same except for the sign over here. All right, so we can just rewrite this equation. All right, so the equation of motion for cases 1 and 2 can be simplified as just one equation that will be mx double dot plus kx plus mu mg, and now we're going to define a function that's going to be called sine of x dot. Equal to 0. Okay, and I explain now what is the sine of x dot. All right, where SGN of x dot is called the signum or the sine function, okay? All right, so let me just specify and then I do a little figure. Figures are always better than to write stuff. So sine of x dot equal +1 if x dot is positive, and obviously sine of x dot is equal to -1 if x dot is negative. All right, so this will be V, this will be X, this will be X dot. Okay, so what does that mean? All right, if we look at the motion of our system here, you agree this is going to oscillate back and forth to the left until it's going to stop, no? All right, due to the friction. So if I just plot one cycle, this could be something like this, but I understand that the amplitude is going to decrease, okay? But that's not the point over here. So we know from the previous section that this will be one cycle or one period if you want, but that's not the important part. The important part here is to see what? Is that during this part of when the object is going from this point here to this point here, what is the velocity? Too small. The velocity is positive. Okay, I know I did it too small here. What it means that from here to here, the velocity is positive, and from here to here, the velocity will be negative, no? So basically that means that the sign over here, sign of x, should be positive during that segment, negative during that segment, and then positive again. All right? So when you define over here. Okay, so I do this in order to introduce you to something, okay, that is important for this class. All right, so the above equation of motion, this equation over here, is nonlinear and a simple analytical solution does not exist. Okay, so the above equation of motion is nonlinear and simple analytical solution does not exist. However, a solution can be obtained using numerical methods. All right, so before doing the numerical solution, let's just look at, that way I don't have to plot it on the notes, I'll give you this page, but what do you estimate to response to look like? So we agreed that due to the dry friction of the Coulomb damping, the response is going to be down. Okay, it's going to go down. Okay, so this will be again one period, and on each period, how much is the amplitude going to decrease? You could do that. There's some simple calculations, but that should decrease about 4 mu mg divided by k. All right, and if you read this, the equation of motion is nonlinear with Coulomb damping, while it's linear with viscous damping that we did before. Okay, however, the shape, if we divide everything by n, we can find the natural frequency will still be unaffected because the natural frequency is only in function of the stiffness of the spring and the mass, no? okay? So you see the natural frequency is unchanged. Then the motion is still periodic with a vibration back and forth around an equilibrium point, same as before. But now what they tell is that in each successive cycle, the amplitude of the motion is reduced by 4 mu mg divided by k. That's not difficult to derive, all right? If you want, we can do it later. But really the interesting part is to solve the equation numerically, all right? So the amplitude reduces linearly with Coulomb damping, while it reduces exponentially with viscous damping. That was the magnitude. The positive, where the object stops or its equilibrium position, could potentially be at a completely different position than when initially at rest because the system is nonlinear. So basically, when it goes up, it has friction, comes back friction, it's not going to stay at the same point, no, all the time. The point where it's going to start going back and forth is going to change every single time, okay? That's why the system is nonlinear, because it's in function of the position. All right, so I put that to the notes. So it would be 41, 40, 42, 43. I put this page. Now we go to 44. All right, so numerical solution. All right, so I think the best option here is, instead of doing everything theoretical, is just to do an example right away, so you have something concrete, all right? So consider the following single degree of freedom with Coulomb damping. So basically it's the same figure, but let me redo it. I like figures. This is K, this is M, and here we have friction coefficient mu. Okay, so I'm not going to redo the derivation. So the equation of motion is given by the equation we just derived. Oh, maybe, okay. Leave some space over here, mx double dot plus kx plus mu mg sine of x dot equal to 0. Okay, and in this problem, let's select the data k equal to 200 Newton meters, mass to be equal to 10 kilograms, and the damping to be equal to 0.5. And we're going to solve for the initial conditions because there's always initial conditions. Instead of solving for the constants, we need to say to the solution, you need to start from a certain point. We say that at x at t equals 0, this will be at 5 meters. So we put it 5 meters here before we release it. And at the time that we release it, let's say the velocity will be 0. So it will be 5 meters, 5 meters second. Okay, so this is pretty easy to do in MATLAB, but at least let's do it once, okay? Once you do it once, you just need to modify your little function over and over. All right, so the whole secret is to rewrite this equation into the state space representation, okay? So you want the trick is to write the equation of motion with the state space representation. Okay, so in order to do that, you need to assume, I mean, it's very easy, okay? Let's assume y equal to x dot. Okay, and z equal to x and x dot, or you could write this as being equal to x, y. Yes, if y equal x dot, this will be our solution. Okay, so if we have this, then what could you say? That z dot should be equal to what? X dot, yeah? Or could be equal to x double dot. Or now, this could be equal to what? Y, because x dot is y, and x double dot. All right, so here you need to pay attention to the z. That's the whole thing. Okay, so we can go here to rewriting. The equation of motion. Okay, let me do the, I don't know, the first time I just do with you every single step. Mx double dot plus kx plus mu mg sine x dot equals 0. So basically here, the only thing we need to do is to write that x double dot will be equal to what? Minus, should be equal to minus k over mx minus mu mg sine of x dot Or you could write this as what? X double dot equal to minus K over M. What is X? X is the Z, should be Z1, no? Yeah. And then we have minus mu mg sine and X dot. What would be X dot? X dot would be this one over here. Z2. So guys, yes, good correction. When I divide here by M, this M disappears. So this M disappears. So here it's mu G sine of Z2. All right, so the whole thing is this. All right, so we're gonna here. Okay, so knowing this, I'm gonna have to go to the next page. It would be good if it was on the same page, but let me try to keep it over here. $45, all right. Okay, so let's say from previous page. We can have that Z dot equal to Y X double dot is equal to what? Is equal to Z2, and that the X double dot is everything we just derived is equal to minus K over M Z1 minus mu G sine of Z2. Okay, guys, so let's try to do very quick here. Maybe we can use this one, the last script. I never use it. Let's try it. Things you can type it. So let's say here, when I like it, slow. Something I don't like already is. All right, so I guess I can type here, let's say, numerical solution. Coulomb free vibration. All right, so now let's define I mean, personally, when I solve a problem, I don't want to go to the line. I don't want to write more tests. I'm not liking it already. Huh? All right, so basically we need to put here the percentage sign. M will be 10 kilograms. What else do we have is K will be equal to 200. So 200. And that mu, the coefficient will be 0.5. So let me do one thing here. I like to do that personally in all my codes. Is before I start everything, let me clear all the variables and I clear the screen, okay? CLC. And now we can start the program. So I'm going to do it just like if I was on the other editor. All right, this one. This is the data. So let's call this one. I'm going to use this one, input data. All right, next thing we need to do numerical integration input data. Here there's multiple ways to do it. I don't now I'll probably change it, but let's say the way I have it on the notes. Let's say you select a time step equal to 0.05. And let's say you want to run the solution for, I mean, you can change that, okay? You can put the total time instead of doing this. 100 and, okay. You want to run everything. So here, sorry, this will be number of points will be n equal 160. So really the total number of times you will have, your maximum time you can run is dt times n. But I mean, you could put directly what you want for Tmax. Okay, I don't think you need to do that. So now your T-span here, the total span that you're gonna have of time, you will start from 0. You have a time step of dt, and you go to Tmax. I will give you this anyway, okay? I'm just doing exactly as it is. Probably I would do it differently. If you ask me, I would not put the n equal 160, I would just go directly to Tmax, no? To define it, but I mean, since I'm gonna give you that file, let me just do it as close as possible. All right, so now let's just go here. All right, let's say we go here to the main program of the program. So this is the part you should not really modify all the time. So okay, to make it fancy, let's say display numerical solution. So the output we're going to be solving is T Z equal ODE 2, 3. You have different ODs, but it's just 2, 3 here. And then this is the stuff you're going to have to define. This is the only thing that needs to be changed. D function 1, and I will do it in a minute. And you run the solution between T-span and Z0. Okay, so I forgot to define that, which is important. Okay, so numerical integration. Yeah, this is important that I put this. So hold on 1 second, numerical integration, go back over here and put initial conditions of your solution. So we know that x naught is equal to 5. And we know that v naught, which is x dot, equal to 0. So that means that our initial condition here, z0, is equal to a vector that will be x naught, v naught. All right? And basically we're almost done. Really, we are done here. Then I will show how to do the rest. What we need to do here, let's see, we're gonna save that file. So let's see over here, let's say MATLAB. All right, let's say here. Let's just go one Coulomb, numerical integration, save. Okay, the important part here is that now you need to create a new function, so new script, or it should be a new function. Does it give you the option? I define the option from 0, okay? For me, it's easier. So now defining the function, we're gonna have, so function f equal the function 1, and the two variables we're swapping is what? T and Z. Okay, let's see if this MATLAB is smart or is like the old ones. I think we might have to put the data over here. All right, so let me just do this. We can change this later on, but let me just rewrite the data here very quick, and then I will make the change. K equal to 100, mu equal to 0.5, and on the equation, we're also going to need G equal to 9.81. All right, so now, only part to be modified. Okay, this is the important part. Everything else is very simple. So over here, what we have? We define a function f that will be initially 0 to 1. Now, basically, the f is our z. So we know that f1 is equal to what? Our z is our f. So the 1 should be equal to z2, no? Yeah, and the second one should be equal to this one. So that's what we do here. Here we'll have f1 should be equal to z2, and f2 should be equal to minus k over m times z1 minus mu times g, and MATLAB has a function called sine, which is called sine over here of z2. I think that's it. That's what we need to do. Did I forget here a parenthesis? 1, 2, 1, 2 looks fine. So why? So file, save as. I need to put it on the same space as the other one. Okay, so it should be the function 1 and save. Okay, so now let me just do the first one, then we can do the rest. So this will give you the solution. So now the output, you can put whatever you want. So let's say the first figure 1 that over here will be, okay. All right, let me do the same thing that I have there. So I have to subplot 1, 3, 1. And on the subplot 1, 3, 1, I do plot the time with the solution that is Z of the first column. And let's see what would that give us. And let's say grid on. All right. Now, subplot one, 3, 2. Can do copy paste here because it's pretty good. The same thing. Z2. All right, and here, let me just do a bit better. I forgot X label. So the X will be the time in seconds. The Y label will be the displacement or response in meters. Okay, the second one will have basically the same thing, time, but this time this would be the velocity in meters per second. And then the last one should be, so Z1, Z2, okay. All right, so all right, so hopefully this will work here. So there's an error somewhere. F eval, so that's not good to have it right there. D funcs one, so it's not, it's right here, it's on the same folder. Oh, let me say this differently. I'm not like, I don't like this stuff here. I'm not familiar with that, so let me just call it MATLAB code M. What do you have all those 3 different extensions here? Let me do something here. I'm not familiar with the MLX. I don't know what I wanted to try today. All right. So how do we call this file? Numerical solution Coulomb. Save. I don't like the MLX. I'm not familiar with. So now this should work. No, same problem. Okay, so let's just say after some debugging, we got the solution. So this is response with respect to time, velocity with respect to time, identical, but you see the amplitudes are different. These solutions start from the initial condition 5, and this one starts from the initial condition of 0. And then I like more this one because we start from here, which is 5, 0. And as we move along this curve, you see the amplitude becomes smaller and smaller. So we go once, 2, 3, 4. So 1, 2, 3, 4, 5. At the end, we'll see would be the response equal to 0. All right. So let's look again at the code very quick. I will give you this code, I don't mind, or you can rewrite it. I mean, how can I make just to be on one figure? So basically it's here. I think maybe we can check now on how to make these variables common. I know we're able to make these variables that they also be considered within the function loop. So you don't have to redefine them, no? Okay.